Okay,
At least we can see you.
My screen?
Yeah, visible. Make it full screen.
Yeah.
Make it full. Slideshow. Slideshow better, I think.
Yeah. 1 minute.
Slideshow.
This is where? This is 1 minute.
Yes.
Yeah.
No, sir.
Sorry, because it's dark here. Okay. Slideshow is this one, right?
Yes, please. Perfect.
Okay, the full slide is visible?
Yeah, visible.
Yes,
everything is fine. Voice is good.
Okay. Right, fine. So we'll start this.
Yeah, please.
So once again, excuse me for the small hiccups.
No issue.
Yeah. So, right. Now, in this session, we're going to discuss about energy conservation case studies in thermal utilities. So, what is a thermal utility? We have different kinds of fuels available, like coal, oil, or any agro fuel. Different kinds of fuels are available. What is the fuel? Basically, it has got some carbon and hydrogen, hydrocarbon basically, which on combustion releases heat. And in addition, the products are carbon dioxide and water vapor. So the heat that is generated by this fuel, we are trying to use it in different applications to convert a product or run a process. So for various heating applications or melting applications. So the whole objective of energy conservation here has to be approached from what is popularly called the cradle to grave. The cradle is the fuel what we are actually getting. So we have got some fuel, it has got some heat content, some kilocalories, and there is a requirement in the process. We want, let's say, heat water from 30 degrees to say 90 degrees. We got to use this heat. How much heat is actually required for heating up the water? How much heat is liberated on combustion of the fuel? So this is where we are trying to match, exactly provide the right kind of heat or right quantity of heat that is required for the application. That is for heating up the water. As we know, no process is 100% efficient. No conversion is 100% efficient. There has to be some losses. So when you burn the fuel, how effectively we get out that heat content or the calorific value, whatever calorific value is there, the entire heat, we have to bring out that calorific value. And there will be losses in the first combustion process itself when you convert the chemical energy in the fuel to heat energy. That's what we are doing in the process of combustion. Is nothing but an oxidation reaction. We are converting the chemical energy in the fuel. It is there in the forms of various elements, carbon, hydrogen, and even sulfur, a little bit. So all this we are oxidizing. When you oxidize, they burn. And when they burn, they give up heat. So in this process, there is going to be a loss because no process is 100% efficient as per the laws of thermodynamics. So there is a loss in the combustion process. Then there is a transmission of heat. So the heat has to be transferred to the process where it is going to be utilized. So some losses. And the utilization itself, the equipment, when you're heating up the water. For example, the simple application, when you heat up the water, let's say we are taking a vessel and heating up the 1 liter of water in the gas stove in your kitchen. So if you carefully observe, what is the actual useful heat required? That is heating up the water from 30 degrees to 100 degrees or 90 degrees, let us say. You want to heat up the water from 30 degrees to 90 degrees. This you are doing it in the kitchen in a small vessel. If you observe, we are lighting up the gas stove and then the flame is coming, the heat is liberated and where all this heat is going. The heat that is going to heat up the water from 30 degrees to 90 degrees is only one component. Where the remaining heat going, we need heat to heat up the vessel itself. And then there is a loss, that is the surroundings. The ambient air around the flame is getting heated. Whether the flame itself, the gas itself is fully on a combustion mode or not, whether it is fully burnt, are there any unburns in the gas that is coming out of the burner. So like this, if you keep analyzing, the losses can be quite significant. Then this is from the combustion side. You burn a fuel and the losses, unburned losses, the flame heat getting radiated and convected all around the place, the heat required to heat the vessel itself, and then the control part. How do you know that 90 degrees has reached? Suppose if it goes 92 degrees and 93 degrees, unnecessarily you are losing heat. So there is also a control component. We need to have a kind of thermostatic control, which, or even a temperature indicator, where the minute it reaches 90 degrees, we switch off the stove. If it is less than 90 degrees, the process is going to get affected. If it is more than 90 degrees, we are going to waste energy. So that means controls also play an important role in saving up this energy. Then is the vessel closed or not? The heat emanating from the hot water itself. Suppose you provide a lid, we're going to save energy. Suppose you provide an insulated lid, even more energy. If you're going to provide an insulated vessel, even more energy we're going to save. So this is exactly what happens in the industry also. When we approach energy savings in the thermal systems, what we are trying to do is to do an energy balance, starting from the fuel, how much of fuel is burnt, how much heat is generated. Yeah.
Just I will interrupt.
Hello?
Whether you are referring PPT or you are on first slide itself.
Yeah, I'm still in the first slide.
Oh, no issue, sir. Thank you. Please.
So
please.
Yeah.
Carry on.
Okay. Yeah. Right. Now, okay, some changes there in the first slide.
First slide is there.
Yeah.
So I thought
Okay.
you might be referring.
Let me go to the second slide. I've gone to the second slide. Is it okay?
Oh, yeah, it's okay. Fine, sir. I can see.
You can see the second slide now, right?
Yeah, I can see.
Okay. Yeah, because last time it was not moving. Right. So now looking at this, the fuels, what we use, a variety of fuels are being used. We have the petroleum fuels. The petroleum fuels are basically the diesel, petrol, and then industrial grade we use furnace oil. So these are the fuels commonly used in the economy. Either for transport we use diesel, petrol, and then for the industry there are fuels like furnace oil, right? Okay, so now if you see this, now how do we select the fuel? This is again based on the calorific value of the fuel, how much the calorific value, the weight of the fuel, and then we have price. Ultimately, what is the price we pay for the fuel? So all this matters when you track the energy source. Okay. Right. Then we have once you burn the fuel, as we discussed, the combustion, how efficiently the fuel or the chemical energy in the fuel is converted into heat energy. So that depends on the kind of controls you have, the kind of technology you have. And finally, the heat is transferred to some other medium like steam, for example, water becomes steam. So in this case, Just 1 minute. Yeah, right. So in all these things, there are losses that take place in the fuel combustion and in the transmission, distribution, and also the utilization. So at every point, there is a loss that is taking place, and our objective is to minimize these losses. Right. And when we talk about efficiency, there are certain allied factors which also go in. That is, the price of the fuel. What is the price per calorific value? So if you see petroleum fuels, there will be generally about 10,000 kilocalories. Calorific value will be 10,000, and the price, say for furnace oil, it will be around 40,000 rupees per ton. Whereas if you take a fuel like coal, solid fuel like coal, the calorific value will be around 4,000. The price will be around 5,000 rupees. So what we need to do is we also need to find out what is the price, cost per kilocalorie. Whichever is the cheapest, we choose that fuel. So it's not only about energy efficiency, but energy management. So ultimately, the industry is interested in reducing the cost. So we try to select the most economical fuel that will give us the requirements at the least cost. So that also matters in the selection of the fuel. Besides the efficiency considerations, we also need to consider this. And these are the petroleum fuels. We have furnace oil. So the crude oil comes into in the refinery. From the gas well, the crude is extracted, and oil wells, the crude oil comes and then it goes through a distillation column. But different gases, different fuels are separated. The topmost is the LPG, liquefied petroleum gas, naphtha, the fuel used in the fertilizer production, petrol, kerosene, diesel, lubricating. So like this, there are several fuels which are available. The bottommost are basically the slightly inferior fuels, but still having almost equal calorific value as any of these better fuels in the top. These are top fractions, which are lighter fractions and clean fuels. The bottom one will be generally inferior grade, like furnace oil. Further to that is that asphalt and tar. So all these fuels, these are the fuels which can be used for the industrial purpose. This is called the furnace oil. Almost the bottommost product of the column is called the furnace oil. It is cheaper than your diesel or petrol, so it's about 40,000 rupees per ton. Then we have a fuel called LSHS, low sulfur heavy stock. This is basically depends. The sulfur content is important when I talk about fuels, so liquid fuels especially. So we have a crude which is having low sulfur content, which is, if it is the input here, we get here in this part LSHS. If we provide a high sulfur crude here, we get furnace oil. So furnace oil will have about 4 to 5% sulfur. LSHS will have less than 2%. So these are all some of the fuels used, petroleum fuels. Mostly the industries use furnace oil because it is cheaper. Very rarely diesel is used in small applications like ovens or say small boilers where handling furnace oil will be very difficult. We use diesel. So it's called light diesel oil, LDO. The LDO itself is slightly mixed up with furnace oil, a mixture of diesel and furnace oil, LDO. But otherwise, diesel also is used as a fuel in the industry when the application is small or requirements are minimal. This is the coal. Different types of coal are there, and you can see this oldest coal is anthracite. It's remained a long period inside the earth, millions of years. So it's almost pure carbon. Then we have bituminous. It is somewhat high in carbon, but not as high as the anthracite. Then we have lignite. So lignite is a relatively young fuel. Left to itself, another millions of years, this could have become coal, but we have dug up and taken it. So this lignite, there are different types of coal classifications. Calorific value for lignite will be 2500 because it's got a lot of moisture content. And it can go up to 6000 in the case of anthracite coals. But these kind of coals are not available in India anymore because we are used to everything. So what is available is bituminous coal. The calorific value is around 4000. Agrofuels, again, we have plenty of agrofuels in use in India. It's one of the most primitive fuels. Even before we started using the modern fuels like petrol, diesel, and all that. This kind of fuels have been in use conventionally for a very long period. So the commonly used agrofuels, rice husk, that is a top yellow portion of the rice after dehusking. It's a very good fuel, and calorific value 3000. And sometimes handling may be difficult, so we make into pellets like this. Then we have firewood, the very common popular fuel. Bagasse from the sugar cane. After crushing the sugar cane, we get the juice. After the juice is taken out, what is left over is bagasse. So each one has got different calorific values, mostly in the range of 2500 to 4000. Coconut shell is a good fuel. It can go up to 4000. These are the common combustion reactions. As we said, carbon dioxide, sulfur to sulfur dioxide. Hydrogen also is a major contributor to the calorific value. 1 kg of hydrogen results in the formation of almost 29,000 kilocalories of heat. And carbon, 1 kg gives about 8,000. Sulfur also gives about 2000, and this is incomplete combustion. So what happens when the combustion is incomplete? This is one of the inefficiency possibilities. When you don't provide adequate air, carbon becomes carbon monoxide, results just about 2400 kilocalories. What should have been otherwise 8000 when it was fully combustion mode. It's only 2430. So these are basic, and our objective is to maximize all this heat that is liberated for the final application. So how closely we can go to that, we'll see. So in the combustion itself, as you can see, there are these imperfections that take place. Like you can't, when you provide air for combustion, always it is accompanied by some amount of excess air. Some more air is given to ensure complete combustion. So that some more air what is given, that takes away a lot of heat out of the chimney. So that means optimization of the air is a first fundamental principle in energy conservation in thermal utilities. So when there's a fuel, what is the amount of air that is required? Stoichiometric. Over and above the stoichiometric, we give some more air to ensure complete combustion. As we said earlier, that if it is incomplete, it results in carbon monoxide. So there is also a loss. But if too much of air is given, no carbon monoxide, but too much of air is given for combustion, the excess air that you are providing also takes away a lot of heat. That is also a loss. So there is an optimization here that is going to take place. So we optimize the combustion, and that optimization is done by measurement of oxygen in the flue gas. So you have a flue gas analyzer, It shows you the oxygen percentage, and more the oxygen, more the excess air. So we try to minimize the oxygen as low as possible. At the same time, no CO. So that is what is known as a good combustion. So CO should not be there. At the same time, some excess air is given, ensuring perfect combustion. So what is that O2 level? That has to be done through a trial and error. So in the case of say liquid fuel fired boiler like the furnace oil or even diesel, so it will be around 3 to 4%. In the case of natural gas also, it will be around the same, around 3 to 4% oxygen means good combustion. In the case of solid fuel fired boilers, it can go up to maybe 6 to 7% depending on the type of firing equipment that we are using. That means the solid fuels require more amount of excess air compared to gaseous or liquid fuels. And these are the various boilers that are in use. So basically a boiler converts the heat in the fuel to heat in water or heat in steam. So we have traditionally, these are the liquid fuel or gaseous fuel boilers. So flame goes in through the tubes and comes out through the chimney. Solid fuel, we had different types. These are the stoker fired. So coal is dropped here, it moves through a grate, and then it burns, and then the heating coils are here, so steam is produced. So similarly here, this is another version. So there is some turbulence given, sprinkler stoker or spreader stoker. The coal is sprinkled in the furnace, so some turbulence, better combustion efficiency. But what is very popular nowadays is the fluidized bed boiler. So the slight amount of air is given to the coal, increased pressure. So the coal particles keep jumping in the bed. Turbulence creates perfect combustion conditions. So with minimum excess air, you can have complete combustion. So these are types of boilers. And we can see this is an oxygen analyzer, which is important for measurement of efficiency to assess the performance. Now the heat is there in the fuel which has been converted or transferred to steam. So steam itself, if you see, is a very popular medium, a secondary medium, heat carrying medium. We use steam predominantly because it is very cheap, the water is cheap, it's got very high specific heat, and steam contains latent heat which is very significant in the heat transfer process. So what is the latent heat? So suppose here you have the point A. At 30 degrees you are heating the water. So you keep on heating the water. It comes to point B where it becomes steam. So at say atmospheric pressure we're doing it, becomes steam. If you it becomes water, sorry, it becomes water at 100 degrees centigrade. If you further add heat, then that 100-degree water becomes 100-degree steam. So if you see, the amount of heat added in the steam is extremely large, almost 4 times than the heat added for raising this from 30 degrees to 100 degrees. Now, this is 100% steam what you have here, and this portion where a phase change has occurred is called the latent heat. So when you take the steam into any equipment, the steam condenses, giving up this latent heat. So this is very important. We need to understand the fundamentals before we start saving energy. So there are several questions we'll be posing when we go to the industry, and so this understanding the principles. So why this is important? See, if you see this, at 1 bar, this is the latent heat. At 10 bar, this is the latent heat. At 20 bar, this is the latent heat. So at 30 bar, this is the latent heat. At 60 bar, this is the latent heat. So what happens, as you see, if you increase the pressure progressively, the latent heat component keeps coming down. So it becomes less and less and less. So what does it mean? When you take a very high pressure steam to a process, the latent heat available is going to be very less. So the heating, for heating, this is the most important. Sensible heat will heat, but heat very, very, very slowly. Latent heat, quick heat transfer, because there is going to be a phase change. When the steam condenses, it gives up liberal amount of heat quickly. So one of the things what we will see is energy conservation options. You to use the steam at the lowest practicable pressure. Why? Because at the lowest pressure, we have very high latent heat. So 1 kg of steam can transfer almost 540 kilocalories here at this point. Whereas we go for 30 bar steam, 1 kg of steam will transfer only about 490 kilocalories. So there is a reduction in the latent heat that is going to be available. So if you keep on going up with pressure, at one point the latent heat becomes zero, and that point is called the critical point. It occurs at this temperature, 374 and 221 bar, where the latent heat becomes zero. So in a power turbine situation, we are going to use a steam turbine and generate power. In that situation, latent heat is not a criteria. We only want the total enthalpy. So today, nowadays, the trend is to go in for pressures in the power station which are more than the critical point. That is more than 220 bar. So you operate at 240 bar steam, latent heat is zero. And the turbine would like it because there's no chance of condensation. Then you also get a higher efficiency. You have higher pressures, the higher is the saturation temperature of the steam, or the boiling point of steam. And as we know from the thermodynamics, T1 minus T2 by T1, the Carnot efficiency, the higher the temperature, the more will be the efficiency of the cycle. So supercritical power plants are in vogue today. So earlier it was subcritical. Today, all the power plants that are coming up are all supercritical power plants. That means they operate at pressures beyond 221 bar. So efficiencies are higher than the existing subcritical power plants. So here the point C is 100% saturated steam. If you further heat it, it becomes superheated. So superheated steam generally not used in the process. It is used only in power plants. So in the industrial application, you will hardly find the superheated steam being used. It should not be used because there will be a delayed heat transfer. Superheated steam behaves like a perfect gas. So poor heat transfer coefficient, very slowly the heat will be transferred and it will delay the process. So we don't use superheated steam in the process heating application. This is a typical steam distribution system. So we have the boiler generating steam. So steam is coming here and it goes into a vessel, a pan, let us say, a jacketed pan into which the steam will be moving, and inside you have some contents which need to be heated. So how the heat transfer takes place, there's a cold solution inside, steam is coming, immediately steam condenses and transfers the heat to the solution inside. So that means the steam condenses, gives up its latent heat and becomes water, or condensate as it is called. Steam and condensate is called condensate. So the condensate comes out, steam is continuously supplied, solution is continuously poured in, and we draw out the condensate. But when you draw out this condensate, steam also will come. Like you have a coil in which steam is coming, steam condenses, steam condensate comes in, but steam also can come out. But we don't want the steam to come out. We want only the condensate to come out. So we need a special kind of valve which will allow only the liquid, that is the condensate, but not steam. That special kind of valve is called the steam trap. Here what we see is a steam trap. One of the most important components in the steam applications, because when you don't have a steam trap, what will happen? There will be a lot of loss of steam. Steam will keep going along with the condensate, and then the condensation will not be proper. So it will take more time for the process to heat up. And if the trap is not there or if it is not working, the steam leaks. So the waste of steam. So the trap is a very, very important component, and it has to be ensured that trap is working properly. In a big refinery or a petroleum refinery, you will find at least 20,000 steam traps in a refinery. So many traps will be there that the loss itself may run into a few tons of steam per day, per hour. So to avoid that, the steam trap needs continuous monitoring, and the monitoring can be done by several methods. So just by we have this infrared thermometers where you see what is the temperature here. So using the infrared technique, that means if the steam is passing, the temperatures are same before and after. If steam is here, condensate only is flowing, there will be a drop in temperature here. So that will tell you whether the trap is working or not. So like this, there are several methods, even ultrasonic methods for testing the trap is there. So periodic monitoring of the traps itself will give you considerable savings in consumption. So all this condensate gets collected from various equipment, like this is also some equipment using steam. All the condensate is collected and taken back to the boiler. So condensate is nothing but distilled water. You have steam, steam is condensed, it is distilled water. So when you take it back to the boiler, your boiler water quality will be good. So there will be no scaling or other problems associated. So it makes sense, number one. And second thing is it also contains heat. The condensate will be at 90 degrees. So when you take it back to the boiler, the amount of fuel consumption in the boiler will be reduced because already we are providing the boiler with hot water. So the condensate recovery is one of the most important technique in the industry, though of course a lot of awareness has come about. Still, there is a lot of scope for recovering the condensate. Many of the industries still are not aware of the benefits of maximizing the condensate recovery. Now, the steam itself, if you see, we have the fuel here. Fuel is fired in the boiler, so 100% energy it has got, chemical energy. Then it is converted to heat energy, and then about 20% is lost in the conversion in a boiler where chemical energy is converted to heat energy. There's a 20% loss. That means only 80% is the efficiency of the boiler. In other words, the steam carries 80% of the heat in the fuel. So 80% is going through the pipelines. There is again a radiation and convection loss, about 5%, in spite of all the insulation. And it reaches the process. So 75% of the heat in the fuel it has carried has come to the process. As we said, heating up water in a vessel. In that process, what happens? The actual requirement, the product from 30 to 90, you want to heat, the energy requirement is only 35% of the total fuel content. So 35% of the energy contained in the fuel only is required for heating up the product. And so 78% we are putting, but 28% goes off as losses. So we have considered various losses, those losses go off. And another 15%, the steam condenses, the condensate is coming out. So 15% comes out here in the form of condensate heat, which is normally recovered. So 10% goes back to the boiler and 5% is the loss. The radiation convection loss as it goes through the pipelines. So if you see the generation efficiency, 80%. Input 100, output is 80%. Distribution efficiency, 80% is coming and 75% is coming here. So this is about 83%. But the utilization efficiency, so if you see, it's very, very poor. So why the utilization efficiency is only 43%? So this 47% is because of the various losses that take place in the process equipment. So as we have seen that simple case of boiling water in a kitchen, how many losses are there? Similarly, in a process equipment also, there will be many losses. So 47% means only about 53% is the efficiency of the process equipment. That there is a lot of scope for improving this efficiency in the user end. Now let us look at the some of the case studies. See, one is efficiently utilizing the heat. The other possibility is there any heat that is coming out, a waste heat which can be reused or supplemented to some of the equipments? There is also energy saving opportunity that is available in many of the plants. Now, in this case, we have this dryers, two dryers are there, which is basically drying what are known as mosquito coils. So we have a mosquito coil production. Mosquito coils are made, they are damp as they made in a dye. They need to be dried. So the mosquito coils keep going here and they have this heating coil through which steam is supplied. So mosquito coils get dried up. So steam coils, and then they put the hot air. The air will be blown, so hot air will go and dry the mosquito coils. Okay, so it's coming from here. The stamping machine is here, so the direction of the material is this side. Now, in this process, we have seen that the temperature required is about 60 to 70 degrees, low temperature drying. Adjacent, are there any other heat sources that are available? So we find that there's an air compressor, there's a DG set, but DG set is not running often. So you cannot consider this as a heat source. And hot water generator is basically for this application. Instead of steam, they use hot water which is circulated to achieve this low temperature. Now, as we go and see, this compressor is adjacent to the dryer, and there are 4 or 5 compressors in operation. And this compressed air generates a lot of heat. So that heat can be utilized for this drying application. So ultimately, we have made that. So that is one. Then second thing is the hot water. We go to the hot water generator. So in the hot water generator, they are using this this kind of sawdust briquettes. This is agro fuel, a sawdust briquette of this size. So this is the size that they are using. And we found that unburns and combustions was very high. So we asked them to cut it to a smaller size, 2 inches. From the 6 inches, they made it into a smaller size. And this alone gave them a better efficiency. So on calculations, what we have seen is the 9-inch length briquettes are currently used, leading to combustion. High excess air is required. Unburns are also more. And suggested to use short like 2 inches. And later on, they cut that into 2, made it semicircular. So basically, it is reducing the particle size. When you have a lower particle size, then your excess air required for combustion will be less. Combustion will be more complete. Perfect combustion can be achieved. The smaller and smaller the particle size. So we reduce the particle size and we expected a 6% reduction, but the actual what they got was much more than this. So even assuming the conservatively 6% savings, it turns out to be 9 lakh per annum. That's the saving. So by optimizing the fuel size, this is one case. And the hot water generator. So instead of steam boiler, here they are using a hot water generator. It's called a pressurized hot water generator. You increase the pressure of the steam. As you increase the pressure of the steam, then your boiling point increases, so you can circulate the water at a higher pressure and higher temperature. So that is the pressurized hot water system. Okay, and this is the schematic of this. You have the hot water generator, and what we have done is this temperature. The hot water generator is 275 degrees. This is pretty high. So what we did was one more preheater we have provided here. One more heat exchanger. So return water. So this is basically the water circulation system. So water goes in, the sawdust is fired. So hot water at 120 degrees because it is pressurized. So it still remains water at 120 degrees. This hot pressurized water at 120 degrees going to the mosquito coil drying. So here, to take advantage of this temperature, we said, okay, we preheat before going to the hot water generator. It pick up some more heat and then go into the hot water generator. So this is another savings that they could get by providing one more additional heat exchanger. They saved about 34 kgs of sawdust per hour. So that itself gives them about 16.5 lakhs per year savings. So this is a compressor, what you see. An air compressor, the efficiency of the compressor is only 10%. So as you generate air, suppose you provide 100 kilowatt of energy to the compressor, the process of compression, air compression, generates a lot of heat. So almost 80% goes out as heat. So 100 kilowatt, if you're providing the motor, you find 80 kilowatt going through the exhaust air, the ventilation air. Now, what we have done is, so this is at 90 degrees. So 90-degree air is vented out here. And adjacent here, you see this window here. So here is where beyond this wall is the dryer. So all we need to do is to tap this. See, these are the ducts you see. So you have to take this ducts and take it inside the dryer room and put it in the dryer. So many of the energy saving measures require some effort. They are unconventional, not traditional. So when you say put a heat exchanger, that is traditional. But when you talk about this is all custom dependent. So it has to be custom built and requires some effort. So normally people, they don't take chances, but in this case, it's all the dynamism of the management. They said, okay, conceptually it is okay, then let us put it into practice. All they needed to do was to break open this valve, and through this valve one duct was run. All these ducts were connected, and they were able to send hot air to the dryer. So this is the hot water generator, what you see here. Pressurized hot water generator, and these are the mosquito coils which are being dried. And the air compressor heat recovery, that the amount of air temperature was about 70 degrees, which is sufficient for the dryer, and that reduced the heat requirement from the pressurized hot water generator. So that resulted in about 4.8 lakh savings. And the case study, another case study here, what we have is the steam optimization of a process plant. So as we have seen, we always need to look into the process. because the generation efficiency is very high. As we have seen the boiler, for example, 80% efficient. What can be done in a boiler, which is already 80% efficient? Maybe 1 or 2% this way, that way, some gains can be there. A transmission and distribution, the 5% loss is there, already insulated. Nothing much can be done. But utilization, we have seen it is only 47%. So here there are plenty of opportunities available. So that means you have to study the process in detail. Every component of the process has to be studied in detail. What are the various inputs to the process? What is happening to the process? What is the process cycle and process description? So we need to be thorough as the process man who is operating the process. That means it requires some time and effort. So once we are familiar with the process, then you start asking questions. Why? Is it basically it's a why analysis, and then why not this way? Why not that way? So that brings us to several energy saving recommendations. This is a basic process of penicillin G manufacturing, various process, and here we have the steam distribution system. So make a steam distribution schematic. So when schematic is made, and try to quantify as much as possible. Many times it's very difficult because there are no meters in many places. So sometimes the meters are there, you quantify. There are no meters, you try to calculate it. From the heat balance, we can find out what is the steam that is delivered for different processes. So make a steam, and thirdly make an estimate how much probably. If you can't calculate, then you can estimate. If you can't estimate, then you can guesstimate. So, but at least some bad data is better than no data. So you get a rough steam balance here, where all steam is going. You may not be much away from the actual result. So this gives you an indication where all it is going and where to focus. And also related with production. Over a period of time, the energy management system should be able to pinpoint and tell you why some days it is going. This is this specific energy consumption. Okay, kg per production. So this you can see there's a lot of variation here and there, and one is directly you can say that the lesser the production, the more is the specific energy consumption. More number of starts, stops, fixed energy consumption more. So directly you can say that the production capacity is critical to the specific energy consumption. So what are the reasons why there is a so in fact you can trace it back to the manufacturing and why the delays, how to overcome the delays. All this will be part of energy. Though it appears it will be a maintenance related job or production related job, ultimately you suffer on the energy consumption. So you have to work back and see what are all the factors which are influencing the production, and wherever possible we need to provide answers to these also, so that always you get this appears to be fairly constant. The production at this range, it's quite reasonable here. So this has to be maintained consistently. Similarly, for a boiler also, you make a process flow chart. You see what are the various components in the boiler, and make a schematic so you understand the various streams. So in this boiler, we have seen DM water overflow. So as we walk through the plant, we find that in the drain there is some noise of water flowing. As we open the drain, we find some flash steam is there. Slow flash steam is coming out. And when we analyze, we find that it is DM water. DM water is coming from the deaerator of the boiler. That is an equipment which goes along with the boiler for removing the dissolved gases. So the deaerator was overflowing due to a faulty level setting. A level setting had to be changed from 40% to 20%. Somebody has set it at 40 and they did not bring it back to 20. So now the dam water was overflowing. So by just changing the setting, so many lakhs was saved. Now, another more important in this, see, these are all things. Make a flow chart. The first fundamental thing that we are taught: understand the process, understand the interaction between energy and the process, and finally you will come to the various recommendations here. And one of the most interesting implementation of the recommendation was this process integration technique. See, in that process, the penicillin G is absorbed by butanol. Butanol is a solvent. So after absorbing this, it becomes impure butanol. This impure butanol from the process is coming, and it has to be made into pure butanol for the next cycle of the process. Impure butanol is coming, then we put it through an evaporator column, put steam and heat it to about 124 degrees centigrade. So then we cool it. We cool it and then we get pure butanol. All the impurities are removed. Only the pure butanol is coming here. And this has to be stored at 40 degrees centigrade. So the 124 degrees is to be cooled and stored at 40 degrees. Now in this process, interestingly, if you see, the impure butanol, 30 degrees it is coming. You are heating to 124. Again, you are cooling it to 40 degrees. So instead of doing this, why not, so take this impure butanol, this is what we heated, and 124 degrees. Then this impure butanol which is coming next will, if you put a heat exchanger like this, it will get preheated. The incoming impure butanol can be preheated with this hot pure butanol here, which is going to come. Instead of cooler, we are going to do this. So what we do here is, now before going to the evaporation section, we have a preheater. Just somewhere here we brought up preheater. So in the preheater, impure butanol is coming 30 degrees. And here 124 degrees after it has been heated from the evaporator, you send it through this preheater. So incoming impure butanol is heated. And then further, whatever cooling is required, you can cool it with the cooler. So here we are making use of the product to product heat exchange. So the hot product is cooled with the cold product. So you get a double benefit. One is your steam consumption is reduced. So steam consumption reduces, and to 75 kg. Earlier is 130, it is 75 now. Cooling water also reduces. So the pumping power of the cooling water, the entire cooling water energy reduces. This is another simple application where this is a tire molding machine, a tube molding machine. The tube molds are the tubes are kept inside this oven. This molds, and then this will be closed, and then thermic fluid is applied over this, circulating on this section. So as we go near the machine, it was terribly hot. So much of radiation is coming from this this molds. That operator also was finding it very difficult to work in that environment. Then we came there, they were also using fans. It's already hot, and then they are using fans. This hot air is circulating more vigorously. So here what we did was again identify the root cause. Where is the heat coming from? The heat actually you should go to the tube inside the mold. But why it is coming out? Then you attack the root cause. The root cause is that it is coming from the molds. Whatever thermic fluid is going, some portion is going to the tire tube and some portion is coming out as heat loss. Now, can we insulate this mold? So this is not conventionally, nobody has done it. It's an unconventional way of thinking. There is a root cause we identified. What is the solution? We have to stop this heat loss. So this was insulated, and after insulation, so you can see that insulated mold, the mold was insulated, and besides the energy saving, the work environment became better. This is one of the biggest advantages of energy saving. Not only the energy is saved, but several other benefits also accrue. The occupational health and safety improves. Sometimes the production also improves. Quality improves. So there are several advantages of the energy conservation activities that we undertake. And you can see like this, there are obvious heat losses. So there's a textile drying section, cylinder, drying range it is called. Wet cloth comes here. It goes through several cylinders like this, and comes out as dry cloth. So in this cylinder, the steam is sent inside the cylinder. The entire cylinder is hot, 120 degrees. But if you see this portion, the cloth is there only in maybe about 30% of the cylinder width it occupies. The remaining portion is empty. So a very simple suggestion is to hold this cloth for some more time till one more batch comes. So you put one more layer of cloth here, one more batch of cloth, so that it can cover the entire section. So steam consumption can be reduced by 30 to 40% by optimizing the utilization of this width. So one cloth, you put two cloths here. So one cloth. So that means the entire thing is covered, and with marginally more steam consumption, you get one more batch also dried up. And this is another singeing machine in a textile factory where the fibers are to be burned, and you have a lot of hot air coming out and thrown out. And textile industry requires a lot of hot water. So instead of throwing it out, so this is actually the flame. The fiber will be there in the fabric. Small fibers sticking to the fabric, which will be burnt with this LPG flame. And as the LPG flame burns continuously, then there is this exhaust system, which is at 130 degrees or 140 degrees. So you can have hot water generation from this exhaust. And small boilers in some of the plants, they have a lot of waste oil which is available. And in this plant, they were using diesel in the boiler, which is quite expensive, 70 rupees per liter at that time. And we also had a lot of waste oil coming from different furnaces and other equipments. So that waste oil was mixed with HSD and burned with the boiler. So this is another interesting case, increasing the inlet temperature to the steam turbine. See, a very simple case. The inlet temperature to the turbine is made in 500 degrees, though the upper limit for this is 516. So the plant was operating the turbine at 500 degrees centigrade inlet temperature. As we know, in the thermodynamics, if you increase the temperature, T1 minus T2 by T1. So T1 is 500, T2 is a condensing temperature. So the more the higher temperatures limit, the more the efficiency. So what we did was gradually increase the temperature by adjusting the superheater temperature, and finally they made it to 500, and we were looking at 510, but they were able to go up to 506. And additional power consumption, 180 megawatts. So this resulted in a huge saving for the company by increasing the inlet temperature of the turbine. And another probable thing that you will see is a lot of high pressure steam is available, which is reduced in a pressure reducing valve, and so instead of using PRDS or pressure reducing de-superheating station, it's called, where the steam is reduced from higher pressure to lower pressure by a valve mechanism. So throttling is a waste of energy. Instead, we can use some small turbines and that will generate additional power. So in this case, the steam turbine which generated about 380 kilowatts, instead of sending it through the valve, we sent it to a turbine. So about 300 kilowatts, 380 kilowatts of power was generated. So here again, the same capacity utilization concept. You see this entire width of the center in a textile mill. Center is another kind of a drying equipment. So here the cloth goes inside this chamber. About 5 chambers will be there, and then hot air is blown, thermic fluid supplied. So hot air is there inside the chamber. The higher the capacity utilized, the efficient it will become. So here you see the width of this cloth, this width of the cloth. Still about 40% of the width is unutilized. That means you can still push it to this side, push this to this side. One more layer also can be loaded. So there are several opportunities like this that can save energy in the industry. Steam traps. So this is a typical steam trap, what you see here. Now, the trap needs continuous monitoring. So you need to check the trap so that steam is not wasted. There's another plant where the centralized hot water system. So they had a hot water system which was used for all the electrical heaters. In this, there's a small washing machine for components in the engineering industry. After doing all this machining, it contains a lot of grease and oil, so it has to be washed in hot water. So they use 75-degree hot water and wash the components to get rid of the grease and oil. For that, here they were using electrical heaters. So instead of electrical heaters, we have made use of the heat of air, compressed air. Compressed air generates heat, and that heat was utilized in this processes. In the furnace also, again, this is related to, see, the loading itself, the capacity utilization alone, if it is focused, it can give a huge energy saving benefit. So you can see this furnace width is being short because they don't want these things to fall this side. So they have put a barrier here which has reduced the furnace width. So if you want a barrier, maybe 2 inches would have been sufficient. Here about 6 inches they have made it, and then they've effectively reduced the furnace volume. Value engineering sometimes. So here you can see, like we discussed again, the kitchen case. You place a vessel of water and you want to heat it. What should be the size of the vessel? What should be the weight of the vessel? If you take an aluminium vessel, it will be faster. If you take a stainless steel vessel, more weight, it'll take longer time, more energy consumption. What should be the optimum weight? So that was the case here. This is the component. The component's weight is 70 kgs. And the basket which is going to carry it into the furnace. There is a furnace. This is a furnace. Underground furnace, the whole basket will be going inside this furnace and heating will be done to 800 degrees centigrade. So the basket weight is 60, almost equal to the product weight. So can we look at decreasing the weight of the basket? Instead of having a solid, can we have a mesh type of arrangement which will reduce the weight? So even if you reduce it by 20%, it will mean significant savings in energy. Yeah. So this is a fuel substitution case. Electric heaters were used in the canteen, and then The industry had a boiler. They used the steam from the industrial boiler and replaced this electrical heaters. Right, like this, there are several opportunities which are there in the industry. The list will be endless depending on the type of the industry. So with this, I think we will close the session and I request any questions. We've already taken some more time than allotted. So if there are any questions, you can have some questions. Hello? Hello?
Sir, hello.
Yeah,
You are audible, sir.
Yeah, any questions?
I request to the participants, any question from your side, you can unmute yourself and ask directly, or you can put into the chat box.
Excellent presentation, Mr. Nagesh Kumar, and very highly informative and multiple case studies. Thank you. Thank you.
Thank you very much, sir. Thank you very much.
Sir, every presentation will give us so many good insights how to conserve the energy. Last time it was, this time it comes with I think 3-4 decades of experience and so many brainstorming sessions with the industry.
Yeah. See, basically, what I will say is, if you do something with passion, then definitely, everybody can do it. It's not that nothing great. As you can see, all these things are not rocket sciences. They're all very simple. But only thing, we were doing it with passion. So, we go aggressively to see how energy can be conserved, and then that's the result. Otherwise, I think everybody is equally competent and capable, and definitely anybody can do it.
It gives us some different orientation, sir, different kind of the thinking actually.
Yeah, exactly. You have to be unbiased. We always, the people who are manufacturing, they are the best, and they know everything. Of course, we don't question them, but we assume that maybe there are better ways of doing things than what is being done at present. So that is the approach. If you accept everything is fine, boiler is fine, process is fine, everything, they're all expert, they know better, then there's no scope. So we start with the assumption that there is something wrong.
Correct. Great, sir. Great.
Yeah.
Any question from participants, please?
Yeah, even otherwise, if you have any questions, you can write to me, and then we can definitely will answer any of the questions.
Yeah, we'll request participants to put on the chat box or on our WhatsApp group, and that will share to you, sir. And you can respond further. Yeah.
Yeah.
Yes. Thank you. Thanks a lot, sir.